All right, everyone. So it looks like we're all basically here. All right, so looks like we're all here. So I guess let's get started. Let's sort of do a quick reminder of what we were up to, since I don't know, I feel like at least I tend to forget what we were doing the previous day. So very quickly, what did we do? We said dimensional analysis is awesome. We all like it, or at least I do, and that's all that matters since I'm giving the talk right now. Analysis is cool. And so then we were saying, when can we use this to use dimensional analysis? Or in particular, when does dimensional analysis fail? And we can use that to say that we must be missing something, because physics is never wrong. We often are wrong. And so if we're not able to guess an answer from dimensional analysis, it means we're being stupid and there should be something fixing the answer. And so what we started to do was say the cosmological constant, your Lagrangian, can contain a term that is literally just a constant, independent of everything else. And this constant has dimension energy to the fourth, cc to the fourth, and we've measured its value to be about a milli eV to the fourth. And the question is, great, dimensional analysis is awesome, so if you wanted to do dimensional analysis on the cosmological constant, what should it do? You say, well, you go through and you look for all the symmetries or spurions, dimensions under which the cosmological constant transforms, and we're not very inventive people, and it turns out we've only discovered one that's not excluded, which is just the units of energy. That's the only thing that we can say about it. And so we expect it should be some order 1 number times some energy scale to the fourth. But we measure and see that it's milli eV. So why is it milli eV and not any other energy scale in the problem, right? Dimensional analysis, you say you put in the relevant energy scale here, and you should see where the stuff is happening. And as far as we can tell, nothing is happening at the milli eV scale, right? There's nothing special related to gravity or any of its symmetries. And so to make this sort of a little bit more precise, let's sort of talk about the one, I would say it's the only solution to this problem that died honorably. And so it's basically the only thing that worked, turned out to be excluded, but that's how the cookie crumbles. And so we had mentioned supersymmetry. Susie, it turns out you need an additional annoying thing called the U1R symmetry. It's not really important, but the main thing to say about this is in this theory, what happens is your cosmological constant, lambda cc, is basically the Susie breaking minus something like a U1R breaking. And so if both of these are small, in particular, both of these are smaller than the milli eV scale, then there's no problem. And in fact, it obeys a dimensional analysis because what happens at the milli eV scale? Well, Susie appears at the milli eV scale. So experimentally, how does that happen? So let's say I am a Gedanken experimentalist. I've explored up to whatever, the micro eV scale. But I'm good at doing gravitational experiments. And so I discover that the cosmological constant is a milli eV. I say something must be happening at the milli eV scale, right? That's dimensional analysis. You go through, you build a milli eV collider or something, you smash stuff together, and you discover what happens. At the milli eV scale, you go from your theory of whatever, let's say this is, you have some light neutrinos or something, and you discover at the milli eV scale, you discover new particles, which are super partners to the neutrino, and you're like, life is good. everything dimensional analysis is satisfied. What happened at the milli EV scale is supersymmetry now looks like a good theory of the world, and supersymmetry sets the cosmological constant to 0, and it's just a small breaking that leaves it. And so this would be a great thing. Dimensional analysis would be satisfied. In fact, you can even do better. You can explain why, just like the proton mass is much smaller than the Planck scale, you can even explain why milli EV is much smaller than the Planck scale. And so you can really get rid of all non-order 1 numbers from your problem. Great idea. Like I said, only problem is we do not see supersymmetry at the milli EV scale. It is a great idea. It just turned out to be experimentally excluded. Okay. So that's basically what we view a solution to the cosmological constant to look like. We want something that's exactly like this, but not excluded. Turns out, like I had said, we're going to be talking about the cosmological constant because I think everyone needs to fail a few times in their life. And I don't think the cosmological constant is a problem that's basically so hard that if you find a solution, you will become instantly super famous. And well, I hope that happens, but it's, like I said, at least a lot of people have failed on it. And so it's a good place to sort of go through and get some humility. All right, so some of the other attempts that have failed. So you can see how crazy people are willing to go to try to solve this problem, right? When you have no solutions, people will be willing to consider quite insane ideas. So let's sort of slowly go through some of them in no particular order. I guess last time we had started to talk about, I think this is the first time people sort of applied historical solutions to naturalness problem. So historical solution. So the idea of a historical solution is that history matters. And basically, you can sort of know this to be true. Walk into an experimentalist's lab, and you'll find very weird situations. You'll find a scalar, for example, they like to study phase transitions. And you'll discover a scalar whose mass is whatever things, let's say like the lattice scale squared. Usually that's negative, and they do plus the Larmor frequency because they decided to apply a B field. And for some reason or another, this is basically equal to 0. And usually these cancellations are like 1 part in like 10 to the 4. It's quite a strong cancellation between these guys. And so these cancel to within 1 part in 10 to the 4. And so you might be very confused and be like, well, I don't often or if ever see cancellations of this sort. But then you go through and be like, well, some poor grad student sat there for 3 days, non-stop, very, very slowly changing the B field to get the cancellation. And so then you're like, okay, this is not surprising because I know someone had to go through and work very hard to get this cancellation. And so that's the idea of the historical solution, which is context matters. Something is small only, or cancellations you might say are unnatural. They don't really appear in physics, but because of how you got there, in this case being in an experimentalist's lab, it does matter. It's like not surprising to see this cancellation. So how might this work in the cosmological constant? So this is called the Abbott model, and it was the first attempt, and it's arguably still the best attempt. So what they did was, he didn't write exactly this model, but he wrote effectively this model, which is you take a scalar, you take a linear term, again, this is not M Planck, this is just some energy scale, let's whatever, call it kappa cubed times phi, and then epsilon to the 4th sine phi over f. So what they did was you put a linear term in the potential, and then you put some sinusoidal piece. And what this looks like is just pictorially, you get a picture which is the energy as a function of phi. Like this. And if you arrange for this to be very small, delta V, so what is delta V? If you go, the distance here is about F. So if you go F, I guess delta V is whatever kappa cubed F. And so if this happens to be less than, or let's say of order, milli eV to the fourth, what happens? Well, this cosmological constant decreases by milli eV to the fourth, milli eV to the fourth. And as you tunnel from here to there, 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 eventually you reach a point here where you're within a milli eV of 0. And so you can be like, well, wait long enough and you will get the answer you want. And so this was Abbott's idea of just, well, what if you just had a model like this, started at any old random point, and you just waited and waited and waited, and this is us right here. And so this was sort of the first attempt at a historical model. Yeah. Excellent. So let's say this was m Planck to the fourth. Then the closest you ever get to 0 will be of order m Planck to the fourth, right? Because what is the largest you could make this? The largest you could make this if this line is exactly halfway between here and here, right? Then that's the largest value of the cosmological constant you could ever get. And if you want to ensure that there's always something near the observed value, then you should assume that this difference here is of order twice the observed value. So since I'm ignoring order 1 numbers, that's of order milli eV to the fourth. Yeah. Okay. So it was a great idea. There's a reason why the model is named after the guy. But turns out there are a lot of problems, or perhaps like I said before, problems equals opportunities. And so there are a lot of opportunities to try to fix this model. And people have tried to fix this model. Okay, so to get an idea of what sort of things you have to worry about, let's say, what are some of the issues here that need to be resolved? Okay, so on the experimental side, there are 2 issues. One, you'll notice the universe sits over here for a long time and then jumps over here. And so the energy density of the universe is equal to this difference here, right? So what happens is you have an empty universe, eventually you tunnel, the bubbles start smashing into each other, and this vacuum energy difference is of order milli eV. So the reheat temperature of the universe is milli eV. This is as opposed to, let's say, BBN, which is capital MEV. So about 9 orders of magnitude larger. So that's kind of a problem. You got the energy density of the universe wrong by 36 orders of magnitude total. So very experimentally excluded for that. And the second is the universe is non-uniform because tunneling is very, very rare in this model. And so the lifetime of this tunneling event is obviously longer than the age of the universe. Otherwise, this would have happened again, and we would have been destroyed by new bubbles being created and killing everyone. And so this size should be larger than the age of the universe so that it hasn't happened a second time to destroy us. And so this is R greater than 1 over Hubble. today. So it is very non-uniform because if you're sitting in the middle here, the universe hasn't had time to equilibrate and get to the same temperature. If we're sitting here, then this would mean like over there's a bright spot which happened to be where all the energy density of the universe was, as opposed to the uniform situation we see today. So there are two experimental issues that you run into. Turns out this is not super generic in a lot of problems, but this is really hard to get around because you're talking about, the whole point is you're talking about stuff happening at the milli eV scale. The universe was a lot hotter than the milli eV scale, so it's hard to deal with sort of this breaking of dimensional analysis. So that's sort of on the experimental side. Okay, so what about on the theoretical side? Are there sort of conceptual issues that you have to get around in these things? So there are several. So theoretical issues. So there's basically the why now problem. Which you can say, put another way, why did I say that we live right here? We could have lived earlier. We could have lived later. If this just keeps on tunneling down, 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 what's special about here? So all you've done is turn the problem of why is the cosmological constant small to why are you living right here in this special point in time. So you haven't actually solved the problem if you can't explain why now. What's going on right now? So for example, let's say, what would a solution to the why now problem look like? Let's say tunneling just keeps on going like this and then stops here, right? Then it sounds like it's reasonable that no matter whatever happens, eventually you always end up here. And so there's not much of a why now problem. That's not what happens in this model. And in fact, that's not what happens in most of these historical models. And so it's an issue that you always have to try to resolve. And you have to come up with some reason to discuss the why now problem. There are other issues. Let's see. Okay, so I guess I might as well mention it since you will hear this problem associated with basically a huge ton of models. So it's something called the measure problem. Which is, how do you define gravity or probability in an expanding universe? So probability in an expanding universe. In expanding universe is hard. And by hard, I mean we have no idea how to do it. In fact, we don't even know what like a good starting place is. So let's talk about why this is hard. Let us talk about the one experimental fact we know about quantum gravity. I would say we know one thing about quantum gravity. And it's this one fact that makes life extremely hard, which is we look at the universe right now, right? It's essentially the horizon problem. Or rather, the solution to the horizon problem. So we look outside, around, and if we literally just extrapolate the universe back, everything we see, there are, God, I don't even remember anymore. There are like, what, 10 to the 20 odd causally disconnected regions that all have the exact same temperature. Okay, so I don't remember what number it was, but let's pretend it's 10 to the 20. It's a large number. 10 to the 20 disconnected guys all have the same temperature. And so this is very odd. And so what do we know about, however, we assume something solves the problem, probably inflation, but whatever solves the problem, the solution correlates and says that part of the universe, even though it's causally disconnected from that part of the universe, they are correlated, right? The solution of any sort, no matter what you're doing, solution is these 10 to the 20 causally disconnected, at least they look like they're causally disconnected now. Disconnected are correlated. And it turns out this makes the universe, or probability, basically impossible to describe, that correlations between things. To see this, let's say this has, I have, my universe is 10 dice, or 10 coins, let's say even. So the 10 coins, up, up, down, down, down. I guess I'm drawing them like they're spins rather than heads and tails, but whatever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so let's say this is my entire universe. It's finite, only 10 pieces of information, bits of information in it. And you can ask, what is the probability that you get heads versus tails? Well, the first thing you might do is be like, well, great, the probability is 50-50, right? Just look here, half of them are up, half of them are down. But this is a problem if these guys are correlated. Let's say these are all independent, but these are 100% correlated. Then this would say, actually, there's a 1 in 6 chance of getting up, not 50-50 probability, right? And so this means, unless I know how information is propagated as the universe expands, so for example, let's actually develop a model of expansion of the universe here, or expansion of coins, I guess. So expansion of coins, theory 1. Okay, this is not a multiple of 2. Oh well, I guess it's a multiple of 5. So every step, duplicate every coin by 5. Duplicate all coins. So in this case, my universe there started up, down, and you get 50-50 probability. It's 50-50 probabilities of being up and down. Great. Second step, second way of expanding the universe, or expanding my coinverse. Every step, duplicate up times 5 times, and do nothing about down. And then this universe comes from an up, down, 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 and it's whatever 1/6, 5/6 is. So I didn't choose some nice numbers, probably could have done that better, but you can see probability depends on, very carefully, on how the universe expands, or my coins expand in this case. And so unless I know this answer, I can tell you nothing about probabilities. Which means I need to understand quantum gravity. I need to understand how things expand, how things are correlated, how's information and all that stuff happening. And the answer is there are reasonable guesses, but there is no answer to this problem. So the answer is then, this is the measure problem, which is probabilities. We have no idea how to deal with probabilities in a universe where which expands. And the problem is, if you look at, well, I guess I erased it, this model, expansion happens differently no matter where you are, right? This expands very fast. Expands fast. This expands, well, it contracts. Contracts, so it barely exists in some sense. This is like removing coins. Does that mean that it's less likely because there are probably fewer of these guys than these guys? I don't know. And so this is the measure problem. And the only solution is just to assume something about the expansion of the universe and how information propagates. And in fact, we know there's one thing we can say is definitely wrong, which is just because there's more of something does not make it more likely, right? Because like we said, there are these correlations. And so God knows what's going on, but this is basically, where do I have it? The measure problem, right? Expanding universe, here's a toy expanding universe. Absolutely finite, very, very small bits of information. We still don't know how to say a single damn thing, right? It has nothing to do with like the universe might be infinitely large or anything like that. It has everything to do with just when something expands, what happens. And yeah, and so yeah, every sort of thing to do this ends up with really weird results. I think every single example that we know of trying to define how information and all this stuff propagates when the universe expands, there will be at least one or two things that are very weird about it. So, such is life. Yeah. The answer is, so at least in this toy model, what you need to know is what happens to information and things like that as the universe expands. And the answer is, we don't know, because let's say we look in this model. This model has eternal inflation because it just takes a long time to tunnel. And so it lives at any point for an extremely long time. And so this means, what happens if you live for long enough? What happens is, eventually stuff at the Planck scale gets redshifted all the way down to observable scales. And so you have no idea what, you could just assume, oh, actually what happens at the Planck scale is you just generate information and you start throwing them down. Quantum gravity people, like ADS-CFT, a lot of people think that, well, DS space has finite entropy, it has finite things. And so the idea of just throwing in new information willy-nilly from M Planck all the way down to the observed scale and just constantly generating information doesn't quite make sense. It doesn't, like, if that was the case, then things like the black hole evaporation would be non-unitary, because you're sort of just generating information out of nothing. But you can just, but the problem with expanding universes is eventually places where you know your theory breaks down, the Planck scale, eventually gets redshifted to modes we talk about today, right? So let's say the mode we're talking about today, whatever, 1 meter. If the universe had eternal inflation, eventually you go up and that mode was at the Planck scale, and I had to have assumed something about it. And if I'm talking about humans existing on whatever, some planet-wide kilometer scale, then that is going to depend a bit on what you're assuming about gravity. So like, it is true that if you just say, oh, well, maybe the universe never expanded except for from BBN to now, that's not quite enough expansion that sort of you're guaranteed something bad will happen. But yeah. Yep. Yeah. Yep. That's correct, yeah. And so if you had access to the history, yes, you would be able to tell it. And since the problem was essentially, as I just mentioned, sort of Planck scale stuff, or wherever string scale, or wherever the UV cutoff of your theory is, getting redshifted all the way down to whatever, GeV or kilometer scales, we haven't seen all that much expansion. So if we did, it would be quite interesting. And in fact, people have done things like in slow roll, this exact transition where you generate so much information that it's more than the de Sitter entropy is exactly the transition between eternal inflation and non-eternal inflation. And so there does seem to be some connection that perhaps that this really breaks down our normal way of just saying FRW expansion breaks down when you actually go to eternal inflation. Is that really a hard and fast rule? Not entirely sure. All right, anything else? Okay. Great. So this is historical solutions. These issues that I sort of wrote down are going to be fairly universal that you're going to have to try to solve no matter what. And people have tried to solve them, and there sort of been reasonable attempts. Okay, so another overview of, oh wow, I spent a lot of time on this so far. Okay, so let's talk about two other things that you will, well, one you'll have heard about, or rather a lot of people talk about. The other I think is just an interesting point. The idea here is called, what is this? This is the third one I'm talking about. It goes by the name of fat graviton. Graviton. The basic idea behind this is, does the problem exist? And when you say, does the problem exist? The question is, we are all secretly experimentalists, even if we're just theoretical experimentalists. And so the question you can just ask, what is the experimental evidence that this problem exists? Getting rid of all theory bias. And so this is a problem with gravity, right? This issue of how do we measure the CC? It's entirely gravitational. And so the question is, how have we tested gravity? Whatever. So let's draw our tests of Newton's law. So V gravity, we've discovered it is 1 over r up to some thing. Afterwards, we don't really know, gravity is too weak to be seen. So this is r, some distance from an object. What is the closest we've tested 1 over r to? Turns out that it's of order 1 times millimeters, which is order 1 over milli eV. So the highest energies, or the smallest distances that we've tested gravity, these are in fifth force experiments where you literally just take like 2 plates together, measure the force, bring them closer and closer and closer and closer, and then eventually you get as close as you can get, which is of order millimeters. Okay, maybe more like 0.1 millimeters, but this is roughly the statement. And so we've only tested gravity up to the milli eV scale. So what if gravity just stops working above the milli eV scale? What if this is just 0? Or it will probably be more some continuous function, or but whatever. But if you're just at the level of drawing things, what if we just draw this and be like, well, yeah, gravity doesn't care at all about anything distances smaller than a milli eV. And this is the idea of the fat graviton, which is just, strictly speaking, throwing all theoretical biases aside, there is no problem yet. So what's a toy example which has something like this? Well, we're not going to talk at all about gravity because gravity is hard. So a toy example would be something like, let's say you have a top quark here, some very heavy, very small object, and we're looking at the force between two top quarks. If this is 1 over GeV, where QCD confines, there's now like some pion force between these guys. So the long-range interaction between two top quarks is some pionic force, which V as a function of R is just some power law. Bring them even closer, and then this pionic force disappears. It's replaced by your QCD, but the pions at least vanish. And at 1 over GeV, this situation qualitatively changes. There's just some new force here that behaves in its new way. And so it's not, this idea that something might happen is, well, this is sort of an example where something happens. This is not the best example because, well, QCD then continues to grow with 1 over R. This might have been, I don't remember whatever the pion force goes as, maybe 1 over R cubed, R to some power. And so it's maybe not the best example because it continues to grow. But the idea is just saying, yes, there can be qualitative changes in how a force behaves if the force, in this case the pion, has size, in this case 1 over GeV. And so if gravity has some size, then it's possible stuff changes there, and maybe you're lucky. And yeah, so this is the idea of the fat graviton. The problem is fairly apparent, which is there is no model. It's an idea. So the problem or opportunity is just simple, which is no model. We have no math to back up the idea. So no model, no math. It is, we have not been inventive enough to think up of a theory that actually does this. The one example we have that sort of behaves like this is string theory. In string theory, when you get to the string scale, a lot of things turn off. Unfortunately, we have not seen string theory at the milli eV scale, and so that's not much of a solution either. So it is worth thinking, since I am personally a huge fan of, or maybe not fan, but a huge believer in human stupidity, that technically speaking, if we throw out all theory biases, the problem may not actually exist yet, experimentally. And so it could just be that we're just too stupid to know of the proper solution, and maybe as fifth force bounds improve, we will see something crazy like that. And fifth force bounds fall off exponentially, and so this is a very sharp cutoff at where they reach gravitational strength, the bounds. Okay. Last comment. Saving the worst for last. Okay, last thing that I just feel obligated to mention, but I think everyone hates, is, okay, well, that is, yeah. Okay, so I have whatever, 10 minutes, 5 minutes to describe this, and then we can have a break. And before moving on to the Higgs. Okay, so the last solution to the CC that we're going to be talking about is brute force plus anthropics. People will often mistakenly just call this anthropics, but that is entirely incorrect. Anthropics doesn't answer any question. It answers, like I said, the wrong question. So if you want to talk at all and mention it, you have to add something else. So what is the idea behind brute force plus anthropics? In fact, we can even just take the model we had before and apply different logic to it. Here's V, and here's phi. Anthropics is the argument that rho CC has to be less than some number. And so we just say the universe has here, has pieces of it that live every single place here. And our existence forces us to live in a band here, which has small enough CC. Look, I drew a model that has a small enough CC. So we obviously live, I guess, here or here. I didn't draw it very straight lines, but maybe here or whatever. And so this is the idea of brute force plus anthropics, which is just anthropics answers what the value has to be. And then I apply the ugliest way I can imagine getting there and just say I've solved the problem here. All right, so issues with this approach. There are, several things. One thing I don't like is that anthropics tells you the answer, it doesn't tell you how, and you're choosing like the dumbest way possible to go through, which is that, namely that if you want to go from the Planck scale to milli eV, so if you want m Planck to the fourth all the way down to milli eV, you need this number 10 to the minus 120, which means you need about 10 to the 120 different vacua, one of which might, if you're lucky, have the right value of being small enough. So 10 to the 120 vacua, quite unpleasant. Second issue, you can sort of see, looking at this, you can look, I have 3 values, and the question is, why do I live in any one value versus the other value? So that number there is about 10 to the 3 milli eV to the fourth. And so why am I milli eV to the fourth, not 10 to the 3 milli eV to the fourth? I don't know. We're not living too close. We're living a factor of 1,000 away from the anthropic bound. Again, the only anthropic bound I'm willing to consider is Weinberg, because he's the only one who did it ahead of time. Afterwards, you can just invent any old crazy thing to get the number you want. But this was the only genuine prediction. And so why are you 10 to the 3 times smaller? This seems like you're logarithmically close and not linearly close. And so even if you ask me, I can give some math to support it if you guys are interested afterwards. But this actually number that it's 10 to the 3 times the observed value makes me think that actually you're logarithmically close, and so there's probably some log solution just like QCD to the problem, as opposed to just some stupid brute force approach. So I'd say those are sort of the 3 things. And then I guess there's a measure problem as well still. Since this is an eternal inflating universe, I still don't know how to just ascribe probabilities to everything. All right, let's see. I think that's basically all I wanted to bother to talk about this. So any questions before we move on to the electroweak hierarchy problem and the Higgs? All right. So I feel like this is probably a reasonable time to do a quick break, and then we can pick up in whatever 15 minutes or so and start to talk about the Higgs hierarchy problem. Yeah, let's start. All right, everyone. Okay. All right, so we're sort of, at this point, done with the cosmological constant. Like I said, it's a great problem. It's probably too hard to solve. People have done absolutely insane things, like coming up with negative energy to try to cancel things. And so there's sort of, the field is wide open from that point of view. And so now we're going to move on to the electroweak hierarchy problem. And this is a slightly more tractable solution, hierarchy problem. And there are a lot more examples of success and partial success at approaches to this problem. All right, so what is, to zeroth order, the statement of the electroweak hierarchy problem? Statement is we have the standard model, L standard model, which has a term which is the Higgs mass, m squared Higgs squared, and this Higgs has things like gauge couplings, d mu h squared, so this gives you gauge couplings. It has things such as the quartic coupling, and it has, let's say, the top Yukawa, which is the largest one. Okay. And so the reason for this is, again, I said everything is, in the end, a statement about dimensional analysis. And so what can we say about the mass of the Higgs from dimensional analysis? We can do the same thing as before, right? We estimated the size of the electron from things like electromagnetic effects. Let's estimate, or did the same for pions. Let's do the same for the Higgs mass. And so we say the Higgs mass squared, is, let's say, we had said, for example, it's proportional to the quartic coupling. So this is one of the examples we did before, times energy squared. You could say spurions also allow the same thing for gauge couplings. Energy squared, and things, let's say, like the top or Yukawa couplings times energy squared. And so, well, dimensional analysis says whatever this number is, something happens at this scale to make it important. So sort of in the full theory, we guess the Higgs mass, and we know to put in the quartic coupling and whatever that new energy scale is. And so what is the value of this energy scale? This energy, you just plug in numbers, right? There are order ones stuff here, so we can't really say exactly what it is, but it's somewhere between 100 GeV and maybe like a few TeV, right? It's dimensional analysis, so when I say few, it could be 10, whatever. And so this is just, the statement is just like, well, something happens at this energy scale. And, well, did I spell? Yeah, I spelled energy, correct. So what has happened so far? Well, the LHC had said basically, well, not much with caveats, much below TeV. Now, well, this is dimensional analysis. This could be 10 TeV, this could be a few TeV. And so at this stage, we just say, well, we've explored something like maybe half of parameter space of dimensional analysis. We still have some ways to go. So in some sense, this is all there is to the problem right now, which is that, well, it's partially explored. That's that. Okay, now people tend to make a lot bigger deal of the situation than just being like, well, we've explored half of parameter space. And the reason for why you might say worry more than this, right? Because at this stage, I would just say like, yeah, okay, fine, go up to order 1 more energy, maybe order 10, whatever, 100, whatever you feel like it, and then actually establish that dimensional analysis is not working. But right now, dimensional analysis never tells you the order 1 numbers, and so whatever. So why do people worry a lot more? Well, people worried a lot more is because they think that they can guess the order 1 number for some reason. And not only that, they think they can guess what happens at this energy scale. So people are worried essentially for 2 reasons. One, they think they know what the order 1 numbers are. And in fact, if you write down a model, of course, you know what the order 1 number is, right? And 2, they think they know what happens at the energy scale. And again, if you have a model, you can tell me what happens at that energy scale. And the reason why a lot of people are concerned is their favorite models, the order 1 numbers are not in your favor, and what happens at that energy scale is very easily seen and hasn't been seen. And so to 0th order, this is why you will hear a lot of people gripe about it, which is their favorite models are excluded. This is dimensional analysis. Just because one model has 10 there doesn't mean your model might have 3 there instead, right? It's not any statement fundamentally about there is necessarily a problem or whatever. It's just a statement that, yeah, some of the things people like are excluded right now. But these are the 2 things that you need to know if you want to claim that there's a problem. If you don't believe that you can know what the order 1 numbers are, and if you don't believe that you know what happens at the energy necessarily, then there may be no problem at all so far. So if you ever hear people say the standard model is fine-tuned, there are problems, it's because they make some additional assumptions here. Okay, so of course, we're interested in solving the problem, right? In some sense, we're asking I would say there's not much of a problem yet, but we are having a machine that's exploring these energies. What would a solution look like? What does it take to get order numbers in your favor instead of against it? And what does it look like at that energy scale? In some sense, the question for me is an issue of not that there's a problem, but that the LHC provides you an opportunity, and maybe what happens at this energy scale is not what you thought, and so you should be doing something different than what you're normally used to doing. Okay, so let's talk about solutions. I'll probably need a new board for this. Okay. Like I've said a few times, I very strongly believe that our approach to everything should be that we are an average physicist studying an average problem, which means we will probably get an average solution, right? This is, I think, one of the basics of science. A lot of people forget this, but we are not special. And so let's categorize solutions to this problem in this framework of a generic solution that we have seen before because this is a generic problem versus something entirely new and non-generic. So we have sort of generic. So these sort of, maybe you might call them boring if you feel like it, but I would say they are more likely because I'm an average person. I will see an average solution. There are the non-generic. And these are sort of whatever, the alien type solutions to the problem. So these are, if you think you're special and you're going to see a new special solution to the problem. Because like I said, estimating things, let's say like the size of the object using some dimensional analysis, you do this all the times in classical physics, even quite often in quantum physics. So great. Let's just start listing a few of the solutions that people have talked about. And then we'll sort of go over them ourselves. There are things like Technicolor. There are things like composite Higgs. There's things like supersymmetry. There are, whatever, let's say, extra dimensions. Let's see, I have a whole list of stuff. So little Higgs, twin Higgs, blah, 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 Higgs. There are historical solutions. There are relaxation solutions. Relaxation. I must be misspelling something. There are, let's see, human stupidity. There is, let's see. What else did I say? Measure solutions. There are UV IR mixing. Unfortunately, there are anthropics here. God damn it, I keep on breaking this. Anthropics. All right, so great way to make friends. Here is roughly a list. There are dots, since I ran out of energy when thinking of ideas. And so roughly speaking, this is what it is, right? We have a dimensional analysis problem. There are boring solutions that we've seen before, and thus, to me, just experimentally are a lot more likely because things, for example, composite Higgs is that the Higgs has finite radius. Every capacitor has finite radius, and that's what solves things like dimensional analysis problems associated with them. Other things like supersymmetry, extra dimensions, any old Higgs model, basically are very specific new solutions that were designed for the Higgs. If we were lucky, it would be great if any of these guys were seen, right? I would be happy if we were lucky and not the standard physicist and just got lucky that the problem I cared about was the one time in nature that we decided to go at supersymmetry or something like that. I've worked on supersymmetry. I really like it. Doesn't mean that I think it's likely. There are other solutions that we have seen before. Historical solutions, relaxation solutions. And I really dislike the fact that anthropics is on this list, but it is what it is. But thus, these things are just inherently, to me, more likely. Just as I said, because of my belief that we are generic physicists studying a generic problem with generic solutions. Okay, so I'm basically going to be focusing very strongly on this side, because as I said, this is biased, and because if you really care about any one of these other solutions, and even the top two here, there are other people you can sort of get to have some TASI lectures, some GGI lectures, Carges, whatever. There are ways to learn about it, right? These things have been around for, some of them have probably been around since longer than we've been alive. And so there's a lot of ways to learn about these things, right? Okay, so let me just quickly dispense with talking about stuff on this side, just generic, so that you have an idea of what those solutions entail. They're non-generic and aliens, and thus they are very exciting in some sense. So there is quite a lot of fun stuff you can say about them. All right, so let's start with supersymmetry. Susie. This is a lot of work people have done on it. The basic idea behind Susie is the following observation, which is we have the Lorentz group, which we experimentally know is realized in nature. And you can ask, what are expansions of the Lorentz group? So what can you do that does not commute with the Lorentz group? It turns out there's basically two answers. Susie and, well, Susie in extra dimensions and CFTs, conformal field theories. Okay, So SUSY is one of these. And the idea of SUSY is what if there is a fermionic extra dimension? That's all supersymmetry is there's an extra dimension that's a Grassmann variable. Dimension, we usually call it theta and theta bar, which are Grassmann numbers. So they're fermionic, Grassmann. Well, Grassmann, anything squared, theta squared equals 0 for Grassmann. So it's either 0 or theta. So 0 or 1, they're basically just 2 points. In the process, one also turns from a scalar to a fermion when moving along this extra dimension, because you acquire Grassmann statistics. But this is the idea of supersymmetry. Well, I can even sort of say very quickly how it's simple to see that you get fermions and bosons without going into really any detail. Let's say you have a field phi, which is a scalar. Depends on your normal dimensions and your fermionic extra dimensions. Taylor series in theta. Theta squared is 0, so you get phi of x plus, I'm going to call it psi theta alpha. You have to dot the fermionic index into something. You have a scalar, you have a fermion. That's all you really need to know. There are some complications with theta bars and whatnot, but to 0th order, this is all the statement is at a fermionic extra dimension, there's a real part, scalar part, and then something that acquires a fermionic index. It's a little more complicated, but there's plenty of places to go if you want to learn the details. And SUSY, if you want to do anything sort of slightly more formalish, SUSY is a great thing because it actually has so many special things that you can prove a lot of things you can't prove in normal field theory. Okay, so we're talking about hierarchy problem here. So how does the supersymmetry, or in particular the MSSM, relate to all this? Well, again, we can figure out what is the order 1 number and what happens at the energy scale. And so what you do is you say, what you discover is order 1 number is delta m Higgs is 6 m stop squared. There's a log that I'm not going to bother with, but roughly about this. And so you get some choice of order 1 numbers. There's 6 times a loop factor. And so that's the order 1 number. What happens here is the mass of the superpartner. So if this is the top quark, this would be the mass of its superpartner. So that's what these guys are called, superpartners of each other. And this is just the mass of the superpartner. If you decide to add more supersymmetries, you can even get rid of this log if you feel like it. Okay, so you get the order 1 number, and what happens at this energy is you get new colored scalars. And so very easy to produce at the LHC, and thus C. And experimentally, we know the mass of these guys should be larger than like a TeV or so. Basically, the bound on anything colored is larger than a TeV. And so as a result, because we know the order 1 number, we know the bound on this, dimensional analysis essentially has failed. You're going to need a number smaller than what SUSY predicts. And so 0th order, SUSY gets excluded because of this. Of course, you could start trying to cancel stuff against each other. That's not the game we're going to be playing today, right? We want a perfectly natural theory where dimensional analysis doesn't fail at all. Okay, so that's supersymmetry. Extra dimensions is going to be quite similar. It's just a normal, instead of putting a fermionic, a Grassmann number, you just put in something else. And so let's say there are 1,000,001 variations of extra dimensions, but like a stupid one just to see what it's like is you just put a circle extra dimension This is my fifth dimension. It's a circle. I can expand. Well, what is my equation of motion? It's always something like box phi equals, maybe with a minus sign. But you get something like that. And the important part here is that there is a d5 squared phi. And so if it has any shape in the extra dimension, this term acts like an effective mass term, right? It appears linear in phi, and if it's just some number, like 5, you get an effective mass. And so when you expand here, it's circle, so you can expand in sines and cosines. You get things such as the momentum in the fifth direction is like an integer over r, probably a pi or something like that too, or whatnot, but whatever. I'm ignoring order 1 numbers and things like that. So what happens is you get a whole tower of states because you have quantized momentum in the fifth dimension. And so you get a whole, if you're looking at the masses of particles, you have some mass, and then it just starts adding up these 1 over r's contribution. And so just like supersymmetry, what happens is the order 1 number ends up also being something of order the same. And what happens are new particles, which are these excited states up here. And so it turns out those are also colored, but because they come from the same particle, they have the same spin. So for extra dimensions, you get new colored fermions. Let's say if we're talking about the top quark. Colored fermions. Great. We can look for those basically as well as we can look for new colored scalars. And so as before with Susie, this is basically excluded because the order 1 numbers don't work in your favor. And what happens at that energy scale is new particles that are not easy to find, or rather that are too easy to find, sorry. Okay, let's sort of go a little bit faster and talk about some of these. Do I want to talk about anything else on that side quickly? I guess, yeah, I guess I won't bother talking about anything else other than just saying that a lot of these other things are also popular. They're kind of cool as well. And however, that's not just going to be the focus of what I'm talking about today. So I'm just going to move on to the other side of the topic here, which is talking about more generic type things that we've seen before. Okay, so what's first on the list? Technicolor. Okay, Technicolor is a great idea. Turns out to be excluded, but I like it. The idea is, what if QCD happens again? Right, so what did QCD give us? QCD showed that there is a symmetry breaking. What happened was your quark QQ conjugate is not equal to 0. And so you break some of the symmetries. And if you actually look at this actually also breaks electroweak symmetry. Now, the mass it gives to the W and Z bosons is so small that it's not really the important part that we all care about. But if we copy QCD and bring it up so that the VEV here is 100 GeV instead of 100 MeV, then, so you copy QCD with a new Qs equals something like 100 GeV cubed. And great. It would break electroweak symmetry, would give mass to the W and Z bosons, That's all nice and good. So we've seen this before. This is just a way of saying, well, the Higgs doesn't even exist in this theory, right? The radial mode is really not part of your IREFT. And so this has no Higgs, no problem. So that's a great way to get around the problem. Unfortunately, we've discovered the Higgs. So great idea, got excluded, right? I think we would all be proud to have thought of this idea before the Higgs was discovered. A lot of people quite rightly thought that it was a very plausible explanation. But at this stage, we don't even need to go into any of its other difficulties. It's just been excluded because we saw the Higgs. Okay, so that's Technicolor. Let's go down to composite Higgs. All right, so composite Higgs is the idea that, I'm going to phrase it in a classical language, the Higgs has a radius. So it's not a point-like object, it has a size. And what happens at that energy scale is, well, that's when you start to see the finite size, right? A great way to make energies finite is if it's like a capacitor, right? The 1/r divergence just stops when you hit the size of the object. Composite Higgs also has a radius. And so here, sometimes these days, people will call it partially composite, is a variation on the idea. Again, I'm not going to talk a huge bit about this since you can find other approaches. Again, very much like I said by my classical analog. If I had to have guessed myself after Technicolor, I would have said this is the most likely thing because we've seen stuff have a finite radius all the time, and thus it's a perfectly reasonable solution. And the main issue with this is more in the technical details. It is things such as, there are things like, okay, so let's say the radius, how do I say this? The energy scale you get when you put in the order 1 numbers is of order TeV, which is greater than the Higgs VeV, which is 100 GeV. Higgs VeV. And so explaining this extra factor, which is sometimes called the V/F tuning, is one of the things that makes it hard for composite Higgs. What is an easy way to state the problem? Let's go over there. Easy way to state the problem is if the Higgs is pion-like, right? The pion has finite radius, then it's a Goldstone boson. What you should write is things such as like the sign of the Higgs. Psi bar psi. So this is, let's say, y top times some number there. And you'll notice this is to make it pion-like so that it's a periodic scalar. Notice that this is not equal to what you get in the standard model, which is Higgs psi bar psi. There are additional couplings and things like that. And so these guys don't behave exactly like the Higgs, right? So let's say, for example, I expanded the Higgs VeV was pi times f, right? You Taylor series this, you get your Taylor seriesing around the top of the sign. And so this Taylor series has a Higgs squared coupling. It has no linear term to the tops, right? And so this is just a quick way of saying the Higgs does not, in these theories, does not behave exactly like the standard model. And so the more standard-like model like the theory, the more you constrain what this guy is like. And the statement is basically, you can go into more detail looking at examples, but at the 10%, 1% level, this thing has dimensional analysis is failing and you need cancellations. Okay. All right. I'm not going to finish the next one. Okay, so this is basically just the brief introduction into everything that I'm not going to go into detail into. If you're interested in any of them, there are a million ways to find reviews, and you can get people who really go into the nitty-gritty details. Okay, so let's talk first about, we're not going to be able to finish, but let's start talking about, I guess, what I wrote third on the list. This is sort of probably the most popular, well, anthropics people like for some reason, but it is at least one of the more recent things that people have become popular. Yeah. So there are a few ways. One, like here, you can just measure, let's say just like an in-principle way, measure very carefully the Higgs coupling to the top and things like that. You can look at Higgs properties by themselves because the Higgs potential is no longer just Higgs squared plus Higgs to the fourth. You have to write in sines and cosines. And sines and cosines, the mass, the quartic, a lot of these things are related. It's not, you don't have full freedom. So there's that. And then finally, just the way, unlike classical mechanics where an object can just have a radius and then nothing else, like in QCD, what happens is there are also a lot of new particles that appear at this radius scale. It's not just, oh, it has a radius, end of story, let's move on with our life. This radius involves the confinement of some other scale, which means there's all going to be like the equivalent of the rho meson or all the other QCD transitions that you can look for. And often this will involve a lot of things, let's say like colored partners and what colored particles and whatnot as well. It depends on a bit on the details. So you can look for any number of those, and they can all do things sort of how you would look for all equal ways of looking for composite Higgs. If you write down a very specific model, you can say one of them is better than the others, but just sort of in broad strokes, those are all sort of good ways to just say, how do I probe that something has a radius? Is it doesn't interact exactly like a point particle, or there are other physics associated with the radius scale. Yeah. All right, anything else? Okay. So we're not going to finish it, but let's talk about, in order, historical solutions. Okay. So I have 15 minutes, let's say. Am I going to go into the elephant in the room? Whatever. I'll start talking about one historical solution, which is in some sense, I'm going to talk about the model that started people looking for new things along these lines. So the idea is called the relaxion. And despite the fact that it has relax in the name, it is not a relaxation solution. It's actually a historical solution. And so it's a bit of a misnomer, but this is a lot more catchy a name than just saying something is a historical solution. And so branding wins above being accurate. Okay, so the idea of a historical solution is going to be very similar to Abbott. The idea is you're going to have, again, well, let's write it in words first. Many vacua, all with different Higgs masses. Before, we had many vacua, all with different cosmological constants. Now we have many vacua with different Higgs masses. And for some reason or another, history implies you end up in the vacua with the low small Higgs mass. Okay, so let's draw a picture of the idea. The idea, so this is, again, let's say V versus a scalar field, or it's going to be a linear term. You'll start to get wiggles on it. And the basic idea is each of these wiggles have a different Higgs mass. Different Higgs mass. I'll sort of start actually writing Lagrangians and things to justify it, but we're just discovering. We might not have, yeah, we are just talking about things at the sort of pictorial level first to write down the pictorial picture of what's happening before getting into actually backing it up with equations. And you're going to choose parameters and get lucky that this first, or maybe the first two or something like that, has an m Higgs squared, which is much less than the natural scale. And so the idea behind the relaxion is, well, you start at a random point. You could start over here and get unlucky, but if you live in this half of the field space, you go here, you roll down, and then eventually you end up in this minimum. And I've engineered it so that this minimum has a very small Higgs mass. And so if you got lucky and started anywhere in this region of parameter space, you will end up here. And so that's the idea of using history to help you, is anywhere you start off, you roll, and then because of large friction or something like that, you end up here in the first time there's a minimum. Okay, so word level, that's the idea, how you use history to do everything. And you're going to actually have to then justify, how can I make this guy here naturally have a Higgs mass that's small? And I think that's the main thing you have to do to justify this picture. Okay. Any questions so far? Or, all right. All right. Great. Okay, so what is the Lagrangian we're going to look at? We're going to have the Higgs at its natural value, the whatever, let's call it capital M, natural value of the Higgs mass. We want the Higgs mass to change as this scalar, I guess I called it phi, changes its expectation value. So this has to couple to the mass sometimes. Somehow or another, let's just call it kappa phi h squared. And then you can add the quartic coupling for the Higgs if we feel like it. Okay. And great. So that gives you the line there. Now we have to add on the wiggles. So it turns out the trick to doing that is part of why it has axion in the name is couple it to GG tilde. And finally, like I said, we're going to need to write down all terms consistent with dimensional analysis. And by choosing m here to be whatever its natural value is, some huge scale, that is satisfying if it's near the UV cutoff of your theory. We know what happens at that energy scale, which is my theory breaks down. Something new happens. But kappa here, in particular, we haven't written every term allowed by phi here. And so we have to also write down plus kappa phi m squared. So if m is, roughly speaking, the UV cutoff of your theory, then the spurionic symmetry associated with this guy allows you to write this term, and you should write it with the largest possible coefficient possible. So order 1, everything. Okay. Great. Now let's sort of ask what happens as a result. So at this point, I have a line there, and I do not have the wiggles. And I had said the whole point of everything is to arrange it so that the wiggles happen and a minimum appears just when the Higgs mass is of order or a small number. So what does this thing do? I guess I'll really go into it in more detail when I talk about the strong CP problem. But one way to see what this thing does is, okay, I'll be a little bit sloppy, but the end result holds. So let's pretend, even though it's not exactly true, that there's only one light quark, which is the up quark. So let's pretend there's plus mu u conjugate. So I'm going to ignore the complication that comes with the down quark, because at least then it's easier to say what this looks like. I can now do a chiral rotation. U goes to u e to the I phi over f. U conjugate goes to u conjugate e to the I phi over f. So I do a chiral rotation. This has an anomaly. I'm not paying attention to the order 1 numbers, but this sends theta to theta plus phi over f. And if I include the theta term, let's say I choose this such that it's a minus sign. Let's write theta. We can even try to write order 1 numbers if we feel like it, but I'm going to be sloppy about order 1 numbers, so let's not bother with a loop factor. What you can see is you can remove phi from the GG tilde coupling and reinsert it in the mass term. And so let's even say plus Hermitian conjugate here. This looks like now mu e to the I. Okay, fine. 2 phi over f. Again, I'm going to be sloppy, not write order 1 numbers. Eta phi u conjugate plus hc. We know experimentally what does this equal to. U conjugate is equal to some order 1 number times 100 MeV cubed. Right? Experimentally, we've measured it. Let's call this just lambda QCD. And okay. And so plug in lambda QCD cubed. We get V is mu lambda QCD cubed times this plus its Hermitian conjugate. So that's a sine or a cosine, whatever. It's up to some phase. Plus a phase if you want. Depends on the phase of stuff. And in fact, let's even write mu as coming from the Higgs VEV. This is yu, the VEV of the Higgs, lambda QCD cubed cosine phi over f. Okay. So what does then a term of this sort look like? This is, well, this equation is true for large Higgs VEV. Turns out there's some subtlety what happens at small Higgs VEV but it's unimportant. It's going to be small is the main thing. Okay, so I can now draw what what my potential is for phi. V of phi is this linear term there is, now you can ask, there's this Higgs-Vev term, but we're going to be interested when the Higgs-Vev is very small, so just ignore it. And then there's going to be this term plus YU Higgs-Vev lambda QCD cubed cosine phi over f. So what happens when the Higgs-Vev is small? So let's say you have a large positive Higgs mass, and just start drawing what this potential looks like. In fact, actually, let's notice the Higgs-Vev here. Why did I write HU? This is Higgs-Vev as a function of phi, because you'll notice the mass of the Higgs is a function of phi, and thus its Vev is a function of phi. So let's say we're going to have a large part. Let's say the Higgs mass as a function of phi is greater than 0, so that the Higgs Vev is 0. This means that this cosine has a very, very small coupling. To the extent that that equation is correct, the coupling, it will be exactly 0. It's a little complicated when you get the Higgs Vev below the QCD scale, so I'm not going to really talk about that too much. But roughly speaking, that coefficient is extremely small. And so you get a linear term, and that's it, right? What happens when m phi squared of Higgs is less than 0? The Higgs Vev becomes non-zero, and now I have to care about this term up here. And you can ask, well, I'm interested in when minima appear. And so let's just calculate when does a minima appear. Crap, I probably shouldn't have erased this board. Oh well. Okay. When does the minimum appear? A minimum appears when the linear term, when this can compete against this, when you're solving for v prime equals 0, right? You want to solve v prime equals 0, which is kappa m squared. I guess I did a cosine, so there's a minus yu vev of phi lambda QCD sine phi over f is what an over f. This is some order 1 number because there's also a phase here plus dot dot dot. And so you can see this can equal 0 when this term is of order that term. So when kappa m squared is of order, this is mu, lambda QCD cubed over f, minima appear. And so at some point here, when the Higgs Vev is, let's solve for the Higgs Vev, it's of order kappa m squared times f over lambda QCD times y up quark. Your first little dip appears, and you get a minimum. And proceeds. Okay, so if this is naturally, if in my theory this is much less than the natural scale, I have obtained victory and done what I at least sought out to do initially, which is arrive at a theory where the first wiggle has a Higgs vev that is much smaller than the cutoff scale, or where your theory breaks down. Okay, and have I done that? So in other words, am I free to choose the up quark Yukawa to be whatever it wants? That might be QCD cubed. Let's fix the factor of 3. There we go. Am I free to choose the QCD scale to be whatever I want? Am I free to choose FA or F and kappa, whatever I want? And the answer is going to be yes for all of these problems. So FA, the axion coupling, that's this coupling. We can choose this value to be whatever we want as long as, well, the theory becomes strongly coupled at F. So as long as F is greater sim M, we're good to go, because otherwise this would give a unitarity bound of order F. So that's the only constraint we have on F, is we have a higher dimensional operator where our theory breaks down. Choose that to be larger than or equal to my imposed UV cutoff, where I just say my theory breaks down. Yukawa couplings have plenty of flavor symmetries. So I can choose YU what I want because of chiral symmetries. Remember, this is the classic example of delta M is proportional to M, right? So this is another way of saying this is YU is the only thing in the world with units under this chiral symmetry. And so just like I can choose H bar to be whatever I want, I can choose, or meters to be whatever I want. I can choose my units to be whatever I want. I can choose this to be whatever I want. And nature told me that unit number was like 10 to the minus 5. Okay. What about kappa? Kappa, the only term I wrote was this. And again, this is the only term that transforms under the symmetry pi theta of p phi tilde e to the I theta of p h tilde. Just like there was this weird symmetry we wrote before, and this is the only thing charged under it. And so just like chiral symmetry, there's a weird thing where I just say delta k is proportional to k. Another way of saying it is if this term was not in the Lagrangian, if I set k equals 0 or kappa equals 0, phi is shift symmetric up to sort of non-perturbative corrections. And so if it's shift symmetric, no way to generate any sort of corrections to the mass and whatnot. So it can be chosen to be whatever value you want. You might not see people use this all that often. People will use an exactly equivalent argument. Okay, I'm over time, so let me just end with this. You'll sometimes see people go like, oh, I can draw a diagram, phi, Higgs loop, and this generates a term. If I do a UV cutoff, generates a term phi h squared. Got rid of h squared with the UV cutoff squared. This is just a cheap way of doing dimensional analysis without having to go through this rather annoying process. That's the only thing you should take out of these arguments, is that they are a quick way to do dimensional analysis. And so, yeah. All right. I guess I'm out of time. Any questions? Excellent. Hopefully that just means people are hungry and that I haven't lost everyone. All right, so let's have lunch.